When two solid objects, like billiard balls, meet, they bounce off each other. But waves are not solid matter, they are transfers of energy, and that means they behave entirely differently when they collide. Because waves are just energy moving through a medium, two waves can pass right through one another. They can occupy the exact same space at the exact same time, and when they do, their effects combine. The rule that dictates exactly how they combine is the principle of superposition. This is the mechanical engine that drives everything you will learn about interference, diffraction, and stationary waves. You must learn this definition word for the exam. The principle of superposition states that when two or more waves meet at a point, the resultant displacement is the vector sum of the individual displacements at that instant. Every single word in that definition earns its keep. Vector sum is the most frequently dropped mark. Displacements have direction. If a peak of +2 centimeters meets a trough of -2 centimeters, you don't just add 2 and 2 to get 4. Because they are vectors pointing in opposite directions, +2 and -2 add algebraically to exactly 0. To find the resultant wave when two waves cross, we apply this principle graphically. Mathematically, we write this as yr equals y1 plus y2. You simply take the vertical displacement of the first wave and add it to the vertical displacement of the second wave. Let's see this point-by-point addition in action. We start with wave 1, then we add wave 2. To find the resultant wave, we do not guess the shape. We pick a point on the x-axis, read the displacement of wave 1, read the displacement of wave 2, and add them algebraically. We plot that resultant point and do the same for every other point along the axis. Joining these points gives us the resultant waveform. Notice how when two peaks align, they reinforce to create a much larger peak. But if a peak meets a trough, they subtract, causing cancellation. Superposition happens every single time waves cross. But to actually observe a steady, clear interference pattern, the waves must meet a strict requirement. That requirement is coherence. Two sources, or waves, are coherent if they have a constant phase difference. This means that if wave A is pi radians ahead of wave B right now, it will still be exactly pi radians ahead tomorrow. Why does coherence require the exact same frequency? Imagine two cars driving around a circular track. If they drive at the exact same speed, which represents the same frequency, the distance between them stays constant. Their phase difference is constant. But if car A drives slightly faster than car B, it will continually pull ahead, eventually lapping the other car. The distance between them is constantly changing. If two waves have different frequencies, their phase difference fluctuates wildly, and no steady pattern can form. This is exactly why you cannot just place two standard light bulbs side by side and expect to see an interference pattern on the wall. Light from a standard bulb is emitted by billions of individual atoms releasing photons randomly. Because these bursts are spontaneous, the phase of the light changes randomly millions of times a second. Two independent bulbs will have a constantly fluctuating phase difference. They are not coherent, so the pattern blurs into a uniform wash of light. Even if your sources are coherent, you might still struggle to see the pattern. 3 strict conditions must be met for an interference pattern to be observable. First, as we just saw, the sources must be coherent, ensuring the maxima and minima stay frozen in space. Second, the waves must have roughly equal amplitudes. If a bright laser crosses a dim torch, the difference between their reinforcement and cancellation is invisible to the eye. Similar amplitudes provide the contrast needed. And third, for transverse waves like light, they must be unpolarized or polarized in the same plane. Why does polarization matter? Remember that displacement is a vector. If wave A displaces the medium vertically and wave B displaces it horizontally, they are perpendicular. Perpendicular vectors cannot algebraically add to 0. They will just create a diagonal resultant. To interfere destructively and create a dark fringe, their displacement vectors must lie in the same plane. Let's put this into practice with two classic exam scenarios. First, identify the principal. Superposition states the resultant displacement is the vector sum of the individual displacements. At the moment of perfect overlap, we read the displacements and add them, respecting the negative sign of the trough. Positive 3 plus negative 1 gives a resultant displacement of positive 2 centimeters. Normally, meeting an antiphase with equal amplitudes means complete destructive interference, giving a resultant of 0. But we must check the polarization. Transmitter 1 is vertically polarized, and transmitter 2 is horizontally polarized. They are perpendicular. Perpendicular vectors cannot cancel each other out. We must use Pythagoras to find the vector sum. The resultant amplitude is a root 2. They do not destructively interfere. Now for a quick check on the most heavily baited trap in the wave topics. A student defines coherent sources as waves that have the same frequency. Why does this score 0 marks? Pause and think. Same frequency is a prerequisite, but it is not the definition.
Let's review your A-star checklist for this topic.